Good morning. Waiting for my iPad to sync. It's been a little slow the last few days. I think sometimes when I use it too much and I'm like importing and exporting all these files, it just kind of like freaks out on me a little bit. How's everyone doing?
Good. Good morning.
Excited that we only have 2 days left in lecture?
Yes.
Well, while I'm waiting for these notes to sync, anybody have any questions about the quiz or the final or anything like that for this week?
Yeah, I actually had a question about the quiz.
Sure, what's up?
Just question 4. I wasn't really sure which way to go with that. I think I tried the ratio test a couple times, and I don't know, it just wasn't working out for me.
Let me actually, I got a couple questions on number 4, so let me share my screen with that. Okay, so yeah, for number 4, I would encourage you to start with the ratio test, right? The root test doesn't seem quite as appropriate here, but when you set it up, it kind of looks long and gross like this, right? And at first, I think it's like hard because we're used to seeing things cancel a lot, and there's not a lot that we can cancel here. But what we can do is kind of imagine what would happen if we FOILed everything out. Okay, so I'm not suggesting that we FOIL it all out, but if we were to FOIL out the numerator, what would the highest degree be?
5.
If you FOIL out both numerators together.
7.
Oh, 7.
Yeah, okay. So we take sort of like the highest power here, right? And we say, okay, well, if I FOILed those out, I would get this. What about the denominators? What if I sort of FOILed out everything in both denominators? What would the highest power be?
You would get the same, 7.
You get the same, right? So the power on the top and the power on the bottom are the same. Now, let me ask you about the coefficients. What would be the coefficient of the term with the highest power in the numerator?
5.
10.
10 over 10.
Yeah, it's going to be 10 because we have this 5 and this 2, right? So without having to FOIL everything out, I know that the leading coefficient is going to be 10 and that the power on the top is going to be 7. And then I know on the bottom, it's going to have the same power. What can I say about the leading coefficient in the denominator?
10.
It's also 10, right? Because I have this 5 and I have this 2. So we know that with polynomials, and specifically when we have like one polynomial over another, and we're looking for what would be like the comparison between the two, even if we were to FOIL everything out, only the term with the highest power in the numerator and the denominator actually matter. So what we really have is like a 10 n to the 7th, and this would be like a 10 n to the 7th, with a whole bunch of terms after it, but those are the most important ones. And so when we take that idea and we plug in infinity, what we're really having is a situation where we know the horizontal asymptote is going to be at 1 because the ratio of 10 over 10 will give us the 1. Does that maybe clarify how to use the ratio test here?
Yeah, that helps a lot.
Okay. Now, the bad news though is that a 1 out of here is like, well, that kind of sucks for you because it's inconclusive, right? So we get 10 over 10, but we realize that's inconclusive. So to that end, if we use one of the other tests that we've learned in the past, okay, because sometimes that ratio test or the root test is not the most appropriate, even though this is kind of the section we're talking about, we still want to understand how to make those decisions. So I went back and I used the limit comparison test, right? Because I didn't want to worry so much about which one is bigger, my B sub n or my A sub n. I was like, the limit test means that I don't really have to worry about comparing the two. I just need to know what my B sub n would do, and then the rest of it will follow. So when I used the limit comparison test, I had my A sub n over here times the 1 over B sub n. And I got 1 using that same idea, right? Like at the end of the day, I know I'm going to get a 10n to the 7th, and on the top as well as on the bottom. So this time I'm going to get an answer of 1. Now, even though I get the same answer from both methods, 1 for the ratio test is inconclusive, whereas 1 for the limit comparison test is positive. It's finite. So that means that my original series, A sub n, will follow the behavior of my B sub n, which happens to be a P series that converges, okay? So A sub n.
What are answers?
What's that?
Would it be wrong if we foiled? Because I foiled for number 4, and then like was able to cancel some of the.
I don't think things are going to cancel when you foil.
Oh, okay.
Okay. I think that it's not going to cancel enough for it to tell you anything. And it's kind of like we're sort of at this point in your math career, and this really depends how far each individual is planning to go, but we're kind of at the point where foiling out and just like showing someone, oh, I can foil out a million terms isn't really what it's about. It's more about stepping back and seeing the bigger pattern without having to do all of that work. Does that make sense?
Yeah.
Okay. I know the foiling out is like something that like for a lot of us, it's something we know that we can do. It's something that we feel comfortable with, but it's more like imagining what if we were to foil it out? How would that impact our answer without having to do all the little small parts of it? Okay. Were there any other questions on quiz number 14? And Alina, I just saw your question, wouldn't it be 8? It wouldn't be 8 because I'm not foiling the n cubed with the n to the 5th, but I am multiplying the n squared by the n to the 5th. Okay. All right, so I'm gonna go ahead and reshare my screen now. My notes have synced, so we can take a look at 11.6 today. Okay, so 11.6 is something called power series, okay? Now, I think one thing that we should kind of keep in mind here is that we are just starting to look at this idea of power series. And power series is something that if you're planning to go through Calc 3 and that's it, that's the end of the road for you, then you probably won't ever come back to look at power series again. And that's fine, okay? If you are going on to classes like discrete or differential equations, then power series will definitely come up again. But I would say the bulk of it is like, if you're like, hey, I'm here to be a math major, and when I transfer from Mesa to wherever I'm going to go to finish this math major, there are some classes that you'll be taking, in particular one called complex analysis. And in that class, you use power series a lot. But it is definitely one of these topics where I'm like, okay, like, I know that for Calc 2, some of us, this is the end of the road. This is it, right? And that's totally fine. And some of us, we got 1, 2, maybe 3 more classes to go. And some of us are in this for the long game because like we really, really love the math. But we're sort of, you know, it's a very large spectrum of who we have in this class and why we need to look at these things again. And so, you know, for those of you who are more like, this is a short-term situation for me, I wouldn't stress too much about it. I would, you know, understand what you can for the final exam, but likely it won't come up again that much in your time here at Mesa. But also, if you're not planning on majoring in math, then it's not necessarily as imperative for you to master this stuff, okay? But let's start with what we know. So what we know, we've learned about infinite series, right? This idea that if you have a bunch of numbers in a row and they all follow a certain pattern and you add them all up together, you can actually sometimes get a value that they all add to, which is pretty cool. And we've talked about convergence versus divergence, but more recently we've specified the difference between an absolute convergence and a conditional convergence, and then having the divergence as sort of this third case, okay? And we've also learned a whole bunch of tests. We learned the divergence test, the integral test, the basic comparison test, limit comparison, alternating series, ratio test, and root test, okay? And I think, you know, again, I sort of shared at the beginning of this section that when I was taking this in my undergraduate, like, it was really hard for me to actually, for the first time, have to feel like I needed to make decisions and make educated decisions rather than just memorizing everything. And so I can see where some of us in this class are feeling like it's just so confusing. And I think that part of that is like, okay, we're starting to look at math in a different way. And that's really all it is. I think it's not so much that each one is individually challenging, but it's putting it all together and looking at it in a different way, okay? But what we're going to talk about today is the power series, all right? So again, power series tends to come up in, if you go higher in math, it is pretty foundational in something called complex analysis. Okay. But for us, what I want us to think about is that we can actually think about some different applications of this. And we'll talk about a few of them before we jump into the nitty-gritty of the power series. But they have a lot of applications in the real world. Okay. And so I think it's almost like whatever we're learning right now is kind of like when you learned how to add or you learned how to subtract. Someone was like, you're going to use this a lot. And you're like, I don't really understand what I'm doing right now. But at some point, there are a lot of applications for it. Okay. So this first section right here is what is a power series used for, okay? So here are a few uses of the power series. So the power series is actually used a lot in computer programming. And specifically, if we think about something that all of us have used with some sort of regularity over the last few semesters, is if we think about our calculator, okay? So like a regular calculator actually uses power series to approximate values. Specifically for e to the x and natural log x. All right, so if you type in e to the power of 2 into your calculator and a number comes out, like, how did your calculator know what number was going to come out? Well, it uses power series to in its program so that it can get really close to a value for what you want you know, because our calculator generally has about like 8 decimal values after that. And then beyond that, it doesn't really give you a specific number. So the programming allows your calculator to sort of more quickly get to this value rather than sitting there and like you type in e squared and the calculator takes like 3 minutes to think about it and then it's like, here's your value. It gives you a value pretty instantaneously, okay? Now, the power series is also used for evaluating integrals and differential equations, okay? So with the evaluating integrals, like the calculator, it helps us approximate values. And it works faster than some of the other methods that we might already know. Okay, so we've learned a lot in Calc 1 and Calc 2 about how we evaluate integrals, but the reality is the ones we've looked at are fairly simple. And when we get into more and more complicated integrals, it's important to think about, well, how can I get to this answer faster? Or if I'm going to program something to do it for me, how can I make sure that the program works as efficiently as possible? So you can kind of tell that approximating values is a pretty important application of this, all right? In the sort of more short term, we use power series a lot in helping us solve differential equations, okay? Because we can actually apply power series to not just integrals, but also to derivatives, okay? Now, I feel like I'm about to crush some dreams here, but you've spent a lot of time very recently learning about integrals and derivatives and like mastering these skills. And I think sometimes when we're like in it, we're like, oh, calculus is like the end all be all. But as it turns out, integrals and derivatives may not always be the most elegant way to approach a situation. And so if you go far enough in math, you'll find that this power series actually gives us ways to evaluate integrals and derivatives much more quickly and in a more, lack of a better word, elegant way than actually integration and derivatives. So there are other ways to solve integrals and derivatives other than what we've already seen, which is kind of crazy, okay? So that's just sort of like a short blurb on what a power series is used for. And I think it's meant just to like, you know, make you think that like what we're learning right here is very introductory, but it does have some pretty cool applications down the road, okay? So if you want to watch some really nerdy videos, if you look up what a power series is used for, there's some pretty awesome people out there who will tell you all about what these power series are used for, okay? But feel free to do that on your own time. Okay, so power series and convergence, that's what we're gonna kind of focus on right now, okay? So here we have what we call a power series, okay? Now, if we were to expand this, all right, let's see what we would get. So by expand, I mean, I would like us to find a sub what? What is the first term in this infinite series?
A sub
A
0.
sub 1.
Sorry, I've heard a couple voices overlapping there. Yeah, the first term would be a sub 0, right? And that's because our bottom index, n, equals 0. So let's write this out. Like, what would the first term be? What would the second term be? What would the third term be? What would the fourth term be? And then kind of take a break and say, what would the nth term be? Okay. So a sub 0, that means I plug in 0 everywhere I see an n, okay? So what does that give us?
1.
0.
C to the 0 times x minus a to the power of 0.
Okay, so everywhere we see an n, we have to put in a 0, right? So we're going to put in a 0 here, and we're going to put in a 0 here. So c sub 0 is, I don't know what it is, but it is a constant that we just say is the constant of the 0th term, okay? Now the x minus n is, or x minus a is now to the power of 0. So what does that go to?
1.
Yeah, that goes to 1. So we can say that the first term is just c sub 0, okay? Plus, what am I going to get when I plug in 1 for n?
C to
C sub 1
Yes.
times x minus a.
Okay, to the first power. Oh, I skipped 2. Sorry, guys. All right, what's our a sub 2?
C sub 2 x minus a squared.
Squared, good. And then c sub 3 would be c sub 3 x minus a to the third. And then if we wanted to say any term in general, we would say c sub n x minus a to the n power. And then we could keep going all the way until we got to the end, okay? So a few things here. C just represents a constant, okay? So there's going to be some constant here. And that constant is going to be different for every individual term. It could be the same, but that's maybe by accident or unintentionally. But it could also be different for every single one. And then we're going to be raising it to some power. And so we end up with like a power of 0, power of 1, power of 2, power of 3. We'll go all the way until the power of n, okay? Now, a few things here are different than what we've seen before. One of the things that's different here is that we have an x in our series. So this x is in our series. What that means and how that's different is now we're saying that we can have variables in our series. So before we just had n everywhere. We didn't have n and x. We just had n, and we could just plug things in and call it a day. But now we're adding this idea of a variable in our series, okay? Now, here's what that means. So now when we look for convergence, okay, the convergence of the power series actually depends on the values of x. All right, that is, a power series may converge for some values of x, but it might diverge for other values of x. All right, so now we're looking at a situation where it may converge for some values and not converge for other values. All right, so we're adding a new layer here where now we want to say not just if it converges or not, but it converges under these situations and it diverges under a different set of situations. Okay. So to that end, we need to take a look at these two ideas. There's something called a radius of convergence, and there's something called an interval of convergence. Okay, so for our power series, if we have an interval of convergence, or sorry, a radius of convergence, okay, we're going to call that R. So we're going to let R represent the radius of convergence. Or we can say that there exists a number R such that the power series will converge if the absolute value of x minus a is less than R. Okay, so that's going to be a case where it converges. And it will diverge if x minus a is greater than R. Okay. So we could have a set of, we could have a power series, and if we plug in certain values, it's going to converge. But if we plug in other values, it might diverge. And that's where things start to get more useful. Rather than having something that converges all the time or diverges all the time, sometimes it's nice to be able to sort of have that on-off switch, that sometimes it converges and sometimes it diverges, okay? Now, one thing is that we do need to take a look at what happens when x minus a equals R. In those cases, the power series may converge or it may diverge. And so we're going to have to look at that special case a little bit. Okay. Now, there is something similar to the radius of convergence called the interval of convergence. So that is the interval of all x's for which the power series converges. So the radius tells us sort of like the starting point and the stopping point, like how far you can go from your center. But the interval tells us, okay, this is the start of where something will converge, and then this is the end of where that region will converge, all right? So they're very much tied to each other, and we definitely use our radius of convergence to help us find our interval of convergence, okay? There is this one piece, though, that I want to highlight here because it's something that we can easily forget, but is going to be important towards the end of the problems, that our endpoints of our interval of convergence are going to need to be tested. Okay, so we'll make sure to revisit that and make that a little bit more clear when we get to the problem. Okay, so power series, lots of uses. The main difference here is that we now have a variable in our series. And because we have that variable, we now have a case where sometimes the power series converges and sometimes it diverges. And so in order to figure out where it converges and where it diverges, we need to use this idea of the radius of convergence and the interval of convergence, okay? So I'm sure a lot of that just made perfect sense. So let's move right on to this set of steps that I think will help walk us through these problems. And then we'll take a look at about 4 or 5 examples, okay? So these problems are definitely longer. There's a lot of writing involved, and we do have to go back to a lot of the tests that we learned, usually ratio or root, but occasionally alternating series or limit comparison or any of the other tests that we've used, okay? So to find the interval of convergence for a power series, we can sort of follow these 4 steps, okay? So what we're gonna do is we're gonna find the value for x for which the power series will always converge at. Okay, so what we're finding here is what I like to call the center point, okay? So this we can think about kind of like our center point. Then we're going to use any test that we have in our repertoire, but usually the ratio test or the root test. And we're going to use that test to determine the conditions that make the power series converge or diverge. Okay. From there, we'll be able to find the radius of convergence, and then we'll make sure to find the actual interval of convergence, okay? And we want to be sure to test the endpoint. So one thing I was thinking that maybe we could kind of tie this back to is, do you remember when we were graphing ellipses and like conic sections in general? But we would have maybe an equation like x minus 4 squared over 9 plus y plus 1 squared over 16 equals 1. So if we had something like that, one of the first points that I encouraged us to graph was the center. Okay. Where's the center for this ellipse?
4, -1.
Beautiful, 4, -1. So I'm going to go to 4, -1, and I'm going to draw the center. So 4, -1. So my center is about here. Okay. Just like we started with the center so that we could graph our ellipse, that's kind of what this first step is. Find the center. Okay. Then after we found our center, we kind of graphed our vertices and our co-vertices from the ellipse, right? So let's kind of talk about from this center of my ellipse example, how far do I go side to side from that center?
Side to side will be 3.
Will be 3. Okay, so let me go back and write some values in here. This was 4, -1. So from here, I would go 3 to the right, and I would go 3 to the left. Yeah. So this number 3 is how far you go, right? It's not the starting point and the stopping point, but 3 is how far you go. It's like the distance. So that distance of 3 is kind of like this radius of convergence. Like the radius of convergence is going to tell us how far to go out from our center point. Okay. Now let's go ahead and write our actual coordinates for the endpoints. What's the coordinate of that right endpoint?
7, -1.
7, -1. Good. So 7, -1. And then the left endpoint would be 1, -1. Yeah. So our interval of convergence is kind of like finding your starting values and your ending value for the shape that you're drawing. Does that make sense? So like we use the radius to find the interval. So this interval of convergence, we're going to use the radius to tell us how far from our center point, and then we can add and subtract as we need. So then we know like our interval for this ellipse would maybe be from 1 to 7. Okay. So that's what we're doing today is not related to conics, but I think thinking about like the steps that we have here as sort of a center point, and then finding out how far you go out on either side, or it could be up and down. No, that's really what we're doing when we're finding our radius of convergence and our interval of convergence. Okay. So that being said, let's take a look at example number 1. Okay. So example number 1, we have this infinite series, starts at 1, goes to infinity, of -1 to the n over 4 to the n, parentheses, x plus 3 to the n. Now, I know that this is the power series because I got a variable in there. Okay, it's not a typo. I didn't mix n's and x's by accident. It's intentional, and that tells us that we have a power series. So what I like to do first is, like I said, find the center. Okay, so we're going to go back to the steps and find the center. Okay, And so when we do that, we're going to take our x minus a and set it equal to 0. And in this case, that's going to be x plus 3, and we're going to set that equal to 0. And when we set that equal to 0, we have a pretty straightforward equation, and we can say that x is equal to -3. And that is our quote-unquote center point, okay? But what that means is that if x equals -3, this power series will converge. Okay. Now, let's make sure that it does in fact converge, okay? So step number 2 is making sure that it does converge. There are situations where it might diverge, but we're going to make sure that it converges. And to do that, we're going to use either the ratio test or the root test, or another one if we need to. And then not only will it tell us whether it converges or not, it will tell us the conditions under which the power series converges or diverges. All right, so let's go ahead and take a look at this equation, or this series. Do folks have a strong preference either way, ratio test or root test?
Ratio.
I hear one for the ratio. Okay, I think both of these work, the ratio as well as the root. It seems like we have a couple votes for the ratio, so let's go ahead and do that one. But you could also use the root one for this one, okay? So the limit as n approaches, let me write my L. So L equals the limit as n approaches infinity of, we gotta put it in absolute value. All right, n plus 1 everywhere I see an n. So -1 to the n plus 1, n plus 1, x plus 3 to the n plus 1, over 4 to the n plus 1, times now the reciprocal of my a sub n. So 4 to the n over -1 to the n times x plus 3 to the n. Whew. If that doesn't make you feel like a total grown-up doing math, I'm not really sure what does. Okay, so let's see what goes away. Let's start with the -1s. So I got a -1 to the power of n plus 1, and then on the bottom I have -1 to the n. So when I cancel some things out, what am I going to have left?
-1 to the 1 and x plus 3 to the 1.
Good. All right. So I'm going to cross out this part with this. Okay. And then you said x plus 3 to the 1. Good, because that's going to cancel with that. Anything else cancel?
4 to the... So you
Yeah.
get 4 to the 1 left.
Yeah. Okay. So let's see what we have left. We have the limit as n approaches infinity of n plus 1 is what I have left on the, nope, I got a -1. I have an n plus 1. I have an x plus 3. And I have that all over 4n. Okay. So, 4n, can that ever be negative?
No.
No, because we start from 1.
Okay, n plus 1, can that ever be negative?
No.
No, okay.
Okay.
But this -1 here, okay, so this -1, I can pull out to the front and make it a +1, right? Because the absolute value of -1 is +1. And at the same time, I'm also going to bring the 4 out to the front, all right? So I've got a 1/4 that I pulled out to the front of the limit. The other thing I'm going to take out of the absolute value is the term that has my center in it, or my x plus 3. So I'm going to bring the x plus 3 out to the front, but I'm going to keep it in parentheses or in absolute value because it might be positive for certain values of x, it might be negative for certain values of x, okay? And then when we take the limit of what's left, we've got n plus 1 over n. And that limit goes to what?
1.
1. Okay. So what we have here then is 1/4 times the absolute value of x plus 3. Okay. This is equal to our L.
0.
So L is equal to 1/4 absolute value of x plus 3.
We leave it like that, or do we plug the x in?
Can you maybe hold on to that question for a second?
Yeah.
So with this L, let's kind of revisit from yesterday. With this ratio test, what values of L tell us if something is convergent or divergent?
Less than 1. We convert.
Yeah. So if L is less than 1, then it absolutely converges, right? And if we substitute what we have here, what we're saying is that if 1/4 times the absolute value of x plus 3 is less than 1, then we will get an absolutely converging series. And if 1/4 absolute value of x plus 3 is greater than 1, then we will get a divergent series, okay? And if it equals 1, well, that's going to be inconclusive. So if we want to find our radius of convergence, then we're going to use this part. If we're saying we want to find where it converges, then we want to see what values of x make this expression true, okay? So that brings us to step 3, which is find the radius of convergence. Okay, so we know where we are at the center, that at x equals -3, this series is convergent. The question is, how far can I go side to side and it will still be convergent? And so here's what we have. We're going to take our 1/4 absolute value of x plus 3. We're going to keep that to be less than 1 because that's the context where we know it's going to be absolutely convergent. And we are going to isolate the absolute value. So when we isolate the absolute value, all we have to do in this case is we need to get rid of that 1/4. And so that will give me absolute value of x plus 3 has to be less than 4. Okay. Here's what this means. From the center, okay, and our center is at x equals -3. If we go 4 units in either direction, so we go 4 units left and 4 units right, then we'll get like that unit of 4 will help us find our interval of convergence. Okay. So from our center, 4 units in either direction will give us the interval of convergence. But what that means is that 4 is our radius of convergence, right? Because the 4 tells us how far we should go in either direction, kind of like that earlier example that we had up here with the graphing the ellipse. And Mariah said very correctly, from the center, you're going to go out 3 units in both directions. And that was telling us how far out we had to go to find our interval of convergence. Okay, so let's kind of pause for a moment. We found our center. We found the value where this power series will always converge. Then we used the limit test to help us determine a statement that would figure out our radius of convergence. So whatever makes the L value, or whatever L value makes it absolutely convergent, is the same expression that you use down here to help you find your radius of convergence. And to find your radius of convergence, all you need to do is isolate your absolute value. Okay. All right, so from here, we have one last piece, which is to find our interval of convergence. So we want to find out how far we have to go in both directions, okay? Now that part's not that hard. It's actually pretty straightforward. However, we want to determine when we get to those endpoints, should we have a filled in circle, like it's equal to it there, or do we have an open circle where maybe it's not filled in? It goes all the way up to, but maybe doesn't include that last endpoint, okay? So step 4 is finding our interval of convergence, and again, be sure to test your endpoint. So to find our interval of convergence, here's what we're going to do. We're going to take our expression that we use to find the radius of convergence. We're going to write that down again. Okay, so absolute value of x plus 3 is less than 4. But we're going to break it down into no absolute value, which means that x plus 3 has to be between 4 and negative 4. Okay. And then how do I isolate my x here?
-3 to both sides.
Yeah, you're going to subtract 3 from both sides. You'll get -7 is less than x, which is less than 1. Okay. This is almost the interval of convergence. Okay. So it's really not that much work to go from the radius of convergence to the interval of convergence. What we need to now figure out is this just a less than, or is there an equal sign underneath? And is this one less than, or is there an equal sign underneath? So that's what we're trying to figure out when we say test the endpoints. Like, do we include -7? Does -7 make this power series convergent? And if so, we should put a minus sign underneath. And does 1 make this power series convergent? And if it does, then we should have an equal sign underneath. Okay, so that's sort of the last part of finding our interval of convergence. Okay, so to test the endpoints, here's what we're going to do. We're going to take -7. We're going to plug it back into our original question. So for x equals -7, we're going to plug that in to our sum from n equals 1 to infinity. All of that stuff stays the same. I only plug in -7 where I see the x. So this -7 went in for the x. Okay. And now let's clean this up. So the sum from n equals 1 to infinity. -7 plus 3 gives us -4 to the n. Okay. So when I simplify that, -7 plus 3, I get -4 to the n. And I see this 4 to the n on the bottom, and I'm like, I really wish this was a 4 to the n, because then I could reduce something. And it turns out that we can manipulate it so that it does. And so we'll write this as -1 to the n times n. And instead of -4 to the n, I'm going to write this as -1 to the n times 4 to the n. Okay. And I have that all over 4 to the n. Now, because I split my -4 into -1 and 4, that allows me to reduce here. And it allows me to combine some like terms. And we get -1 to the 2n times n, and then everything else has canceled itself out. Okay. Now, let's think about what we know about exponents. So I've got this -1 to the 2n. Okay.
Alternating series.
What's that?
Will we use the alternating series test?
Equal 1.
Tell me what you mean by that.
-1 to n equal 1.
Yeah, this 2n is always going to be even, right? No matter what number you double an integer, you're going to get an even number. And we all know that if you take a negative number, you raise it to an even power, it's going to be positive. So this actually simplifies all the way down to this. Now, without having to do really any of the fancy tests, I bet you can tell me, does this series converge or diverge?
Diverge.
Yeah, this is going to diverge, right? Because we're just going to keep adding bigger and bigger numbers. So what that means is when we go back to write our interval of convergence, should we have an equal sign or should it just be less than?
Less than.
It's just going to be less than, okay? So that's what that divergence for that endpoint means. Now, we still have to test the other endpoint, okay? So we're going to do the same thing, but we're going to plug in x equals 1. So that will give us n equals 1 to infinity of -1 to the n times n over 4 to the n and I got 1 plus 3 to the n. Okay. So just like before, I take my 1 or my x value, I plug it into the original equation where I saw the x. And then I simplify. So I know that 1 plus 3 is 4, so I've got a 4 to the n on the bottom and a 4 to the n on the top. And so that's going to give me negative 1 to the negative 1 to the n times n. Okay. Now we could do the alternating series test here. And I think right away from that first step, we should figure out that that limit of n approaching infinity is not going to go to 0. So we actually have a divergent other endpoint as well. Okay. So what that means for our interval of convergence is we have negative 7 is sort of the lowest value, but it never gets to negative 7 because we said when we plugged x equals negative 7 back in that diverged. So there's no equal sign underneath. Then I put my x and then I put the 1, and same thing, I don't put an equal sign underneath that less than because it diverges at x equals 1. And so this is our interval of convergence. It happened to be the same as our original, like almost the interval of convergence, but that's not always going to be true. Which is why I've said like a bunch of times, really test the endpoints because, you know, that could change depending on the given sequence, right? Or the given series rather. All right, how are those brains feeling out there?
Yeah.
All right, so let's take a break here. All right, it is 10:28. Let's be back at 10:35. I think the first question is always kind of the longest, and then after that, you know, it's sort of like I think we start to realize, oh wait, I did get this part, or oh no, I actually do have a question about that other part. Okay. And yes, it is definitely a long problem, right? I feel like this is kind of up there with like the rotation of axes kind of questions where it's just like a lot of going through different things. And it requires you to remember a lot of different algebra skills from along the way, all right? So enough of me talking. Let's take a break. Let's be back at 10:35, and then we'll finish up as much as we can of the rest of the lesson. All right, folks. So I know all we did was one problem before break, but we're gonna get through as many more as we can for the second half of class. And with that, I'll go ahead and share my screen so we can take a look at example number 2. All right, so here we have example number 2, all right? So we've got this infinite series, we're starting at 1, we're ending at infinity. How come we couldn't start at 0 for this one?
Because of the denominator.
Yeah, exactly, right? We have 2 to the n, that would be okay with 0. But on the bottom there, we have just an n, so we know it will be undefined if we plug in a 0, okay? Now, it doesn't mean that all infinite series start at like the lowest possible n, but that could give you some sort of like, if you're like, I don't know why this one starts here and this one starts there, sometimes it's just like, it can't be there, okay? All right, so let's go ahead and take a look at this pattern again. So we're gonna find our center. From there, we're going to determine the range of values that make it absolutely convergent, if there are any. We're going to use that to move on to find the radius of convergence. And from there, the interval of convergence isn't necessarily that hard. We literally just isolate our x, but I think the bulk of the work is sort of in this bottom piece where we have to test the endpoint, okay? So let's start off with finding our center here, or rather the value that makes this series always converging. So we're gonna take our 4x minus 8, we're going to set it equal to 0. That will give us 4x equals 8 or x equals 2, okay? And so what this means is we have 2 kind of as our quote unquote center point. We have that as sort of the value that from there, if we have our radius of convergence, we can easily find our interval of convergence, okay? But in order to do that, we want to make sure that it converges. And so again, here, I think we could use either the ratio test or the root test. I chose to do the root test for this one, but again, you could do either one. So let's take a look at what this ratio test would give us. So put in an n plus 1 everywhere we have an n. So 2 to the n plus 1. Or x minus 8 to the n plus 1 over n plus 1. And then I multiply by the reciprocal of my a sub n. And then I think about what will cancel out. So I think that this 2 to the n and that one will reduce. This 4x minus 8 to the n will cancel out with this one. And I think that's it. So I'm going to take the 4x minus 8. I'm going to bring that out to the front because I know that that part depends on the positive negative sign. And then I'm going to explore what happens with the rest of it. So what else do I have? I've got a 2n, which will always be positive, so I don't need the parentheses or the absolute value bars, and I know the denominator is n plus 1. Now you could have pulled the 2 out in front as well, or you could leave it in here. It doesn't really matter. But when we look at this limit, I think we can see that that goes to 2, okay? Which means that L equals 2 times the absolute value of 4x minus 8, okay? And again, if L is less than 1, we know that it absolutely converges. If 2 4x minus 8 is less than 1, then we get absolute convergence. Okay? And that's what we're going to use to help us find our radius of convergence and subsequently our interval of convergence. So to find my radius of convergence, my only goal is to isolate the absolute value. But we're going to add on to that in the sense that in the inside, we really want to have a coefficient of 1 for the x. So what I mean by that is I have 2 absolute value for x minus 8 is less than 1. Okay. So I can go ahead and divide that 2 away. That's fine. But again, if I want a coefficient of 1 for the x, then what I can do is go ahead and factor out a 4. That will leave me with x minus 2 on the inside, which is good because x minus 2, what value of x makes that 0? It's our 2, which is our center point that we found earlier. Okay. And so we've got one more step. We got absolute value of x minus 2 is less than 1/8. That means that my r, my radius of convergence equals 1/8. That if I go 1/8 from 2 in both directions, that will give me my interval of convergence. But of course, I need to test my endpoints to make sure, do I include those endpoints or do I not? Okay, so we've got our interval of convergence here, which is, we're gonna take our second to last expression, the one before we found our radius, and we're gonna take away those absolute value bars and sandwich them between the positive version of our radius and the negative version of the radius. And then we're going to solve for x. So I'm going to add 2 to both sides. That'll give me 15/8 x and 17/8. Okay. Now, those hopefully don't seem like too weird of a number for you, because remember, we said that x was going to equal 2. That's our center point, right? It converges at x equals 2. X equals 2, another way to say that is 16/8. So I'm going 1/8 above that, which is 17/8, and then 1/8 below that, which is 15/8. Okay. So this is almost my interval of convergence. I just need to go back and test my endpoint so I can determine whether or not I have equal signs in addition to the inequality that's already there. All right, so let's test our endpoints. I'm going to test the 15/8 first, and then we'll test the 17/8. So x equals 15/8 means that I'm going to write my original series, but everywhere I see an x, I'm going to put 15/8. So 15/8 went in for the x. Okay, so n equals 1 to infinity. Let's see, 15/8 times 4, that will give us 15 halves. And then 15 halves minus 16 halves will give us -1/2. So I've got 2 to the n over 2 over n times -1/2 to the n. All right, let's see, how can we rewrite this? So I'm going to keep the 2 to the n. I'm going to keep this n. But I'm going to split my -1/2, so it's -1 to the n and over 2 to the n. And the reason why I did that is because I saw this 2 to the n in my beginning term, and now I can cancel those out. Okay. And this gives me -1 to the n over n. Now this, from our work in the last week and week and a half, we know this is an alternating series, but specifically we know it's an alternating harmonic series, and that is convergent. Okay, so we can do the alternating series test and find out that it is convergent. Okay. Now what that means is when I go back to my endpoint for 15/8, this time I do want to include that equal sign, because at 15/8, at an x value of 15/8, it does converge. Okay. Now we need to test the other endpoint. So x equals 17/8. So n equals 1 to infinity, 2 to the n over n, 4 times 17/8 minus 8 to the n. And again, all I did was plug in 17/8 in for the x. So let's cancel a little bit here. I've got 17/2 minus 8 will give us 1/2 to the n. So 1/2 to the n. I can split that the same way I did the last one. 2 to the n over n times 1 to the n over 2 to the n. And those are going to reduce. And 1 to the n is actually just going to be 1. So what I really have here is this infinite series of 1 over n. And we also know about this series. Does this one converge or diverge?
Diverge.
Yeah, this one diverges. Okay, so one of them converges, one of them diverges. And that means when we go back to write our interval of convergence, we want to include the one that it converged, but we do not want to include the one where it diverged. Okay. Okay, so definitely still a long problem, right? I know it's a long problem. There's a lot of different steps here. And I think the part that makes it challenging is we are drawing upon a lot of what we covered in this last section, like knowing all of those tests, be saying like, oh, I've seen this before, I kind of remember what it does, or being able to see it and say, oh yeah, this is a good time for the alternating series test, or this is a good time for the divergence test, or whatever it might be. Okay. All right. Well, let's try another one. Okay. So example number 3, we've got this infinite series of x minus 6 to the n over n to the n. And so we're going to start off by determining where our center point is, right? So we're going to take that x minus 6, we're going to set that equal to 0, and this one is a quick one. We know that at x equals 6, this will always converge, okay? Then we need to apply one of the tests that we've learned to find out what our value of L is, okay? So in this case, we've been using the ratio test a lot, but I think this one might be a good time for the root test, okay? And the reason why I say that is because both the top and bottom are to the power of n, which means if I raise the whole thing to the power of 1 over n, I'm going to get rid of those n. So the limit as n approaches infinity of x minus 6 to the n over n to the n, all to the 1 over n. That's going to give me the limit as n approaches infinity of x minus 6 over n. Okay. Now the x minus 6, like I've done before, I can go ahead and pull that out to the front. And then I'm taking the limit as n approaches infinity of 1 over n. What does this limit approach?
Oh, 0.
Yeah, this goes to 0, right? What that means is L equals what?
0 equal 1. Always convergent.
Yeah, so L is going to equal 0 because absolute value of x minus 6 times 0 is going to give me 0. What that means is this. If L equals 0, then 0 is less than 1. Then this series always converges. So this doesn't happen all the time, but once in a while you encounter a case where whatever infinite series you're looking at does converge all the values of x, all of the values of x. So what does that mean our radius of convergence is?
Infinity.
Infinity.
Yeah, our radius is going to be infinity because it always converges. So it doesn't matter what values we plug in for x, it will always, always converge in this particular case. So what does that mean for our interval of convergence? How could we write that?
All real numbers.
From negative infinity to positive infinity.
Yeah, we could say from negative infinity to positive infinity, okay? So once in a while, you do get to a situation where, okay, you've identified the center, you applied the test, and you get a 0. And all that means is that it's always going to be convergent, and that's okay, that it happens sometimes, all right? Now, you might see some other videos or explanations where people switch the first and second step. So like they don't find the center first, but they find the L value first. I think there's an argument for both cases. I think for me, like when I was first learning these, I found this process to be just really long and intimidating. So for me, that pink step right there, like find the center, it was something concrete. It was something easy that I could do, and it just got me to put something down on paper, so then I felt more confident moving through the other steps. Okay, so that's why I choose to find that quote unquote center first. The danger in that is that you might encounter a case like this one where it always converges, or you might encounter a case where it always diverges. Okay, so in that case, the pink step is kind of irrelevant. But if you want to, you might want to start with the second step where you find your L value first, and then use that to backtrack and then find your quote unquote center point. Okay, so it's okay to sort of switch steps 1 and 2. Really depends on like what you feel like is going to be better for you. Okay. All right. So that was a pretty short one, but let's move on to example number 4 and see what happens with example number 4, okay? All right, so again, I like to find the center point first, right? Because it just gives me something to write down, but it doesn't, that might not be true for you. So you're welcome to put this as your second step. But in this case, what is the expression that I'm setting equal to 0?
X equals 0.
Yeah, it almost seems too easy. There's no like x minus something or x plus something, but it just means that in this case, x equals 0 is considered our quote unquote center point, or the value that will always make this series converge, okay? Now, from there, let's find our L. And so in this case, do we think ratio test or root test? What do we think?
Root test.
Yeah, I think the root test, just because they're both the numerator and the denominator are raised to the power of n. So I have, let's see, x to the 2n over negative 3 to the n, and I'm raising that to the 1 over n power. So that's going to give me x squared in the top over negative 3 in the bottom. And so in this case, I have 1/3 x squared, and then that's what I have. So the n value doesn't actually impact the end behavior of this particular situation. All right, so we've got our x squared over 3, or we could say 1/3 x squared. And again, that is our value of L. So in order for this to be convergent, we need to find out when does x cubed over 3, when is that less than 1? Okay. How come I don't need an absolute value bar at this stage?
Because it's gonna
Don't have that.
Well, we don't have the n, but we also have a situation where x is squared, right? So that's always going to be positive, so we don't need to worry about the positive or negative case of that, okay? Now, if we kind of start to isolate the x, we get x squared is less than 3, okay? And from here, we get absolute value of x has to be less than this square root of 3. Okay, so this one's a little different because we sort of introduce the absolute value bars towards the end when we need them, because we know when we take a square root, we could have a positive version or we could have a negative version. Okay, so in this case, our r equals root 3. So from my center point of 0, I could go plus root 3 or minus root 3, and then that would give me the values of x that make this particular series convergent, okay? And so the last thing I need to do is to figure out what my interval is and test my endpoints.
I think it's number 4.
What's that?
I think it
Oh,
number 4, the circle. That's all.
sure is, sure is. Okay, so now we're on step 4. So I'm going to take this second to last step. I'm going to split it. So I've got x is between negative root 3 and positive root 3. Okay, so that is my almost interval of convergence. I just have to determine, do I have equal signs underneath these or not? All right, so let's test negative root 3. So for x equals negative root 3, we're going to get negative root 3 to the 2n over negative 3 to the n, right? And let's see what that gives us. All right, negative 3 to the 2n, what does that simplify to?
Root 3 to 2n. It's gonna be positive always.
It is going to be positive, good. But
It'll be 1 to the n.
Can we split them in 2? Like 3 and then 3 to the root 3 to the n. Negative 3 to the n.
Yeah, root 3 to the 2. What does that give us?
3.
So I really have 3 to the n on the top. Okay. Now, knowing that I have a 3 to the n on the top, how can I be clever about splitting my denominator?
-1 to the power of n and 3 to the power of n.
Beautiful. Okay. So that's how you make that decision, right? It isn't that people walk into a problem and they're like, oh yeah, I just know that I should do this. But sometimes just by looking at like one part of it, you can use that one part to direct your next steps, even in simplifying that same expression. So by being clever like that, we've got our 3 to the n and 3 to the n that reduce. Okay. Now, what does that give us? This gives us nothing more than -1 over -1 to the n. But what's another way that I can rewrite that?
-1 to the negative n.
-1 to the negative n. I could write it like that, but what's maybe an even better way to write that?
One over -1 to the nth power.
Okay, and what does that give you?
-1.
What happened to your n?
Ooh, anytime you multiply 1 by itself, it's 1.
You said this, 1 over -1 to the n. And you told me that that reduced to -1. I don't buy that.
-1 to the n.
-1 to the n, yes. So net n equals 1, and I get -1 to the n. Now, -1 to the n, if I just write out a first few terms, I get -1, +1, -1, +1. Those are the only values that come out of there. It doesn't matter what values of n I plug in, there's only 2 possible outputs. So I know that this one diverges, okay? Which means I do not want the equal sign underneath this one, okay? I'd like you to try plugging in x equals +√3. Okay, work through that one. I'll give you a couple minutes to work through that one and see what you get, whether we should include an equal sign underneath that less than or just keep it less than. All right, so when we plug in a +√3, because we ended up squaring it, it actually gives us exactly the same thing as we got for the first endpoint. which means that both endpoints are going to diverge and therefore should not be included in the interval of convergence, okay? So in this case, like our first example, we just have less than symbols. We do not need the less than or equal to because both endpoints diverge, okay? Any questions about example number 1?
And we said it diverges because it's alternating from negative to positive, correct?
Negative to positive 1.
Yeah.
Okay. Because there are alternating series that will converge. But you could also use the alternating series test here. That would be another way to justify your answer. Any other questions on example number 4? Okay. So we've got one last example here, right? So we've got this infinite series. This time we're starting at 0 of n factorial times 2x plus 1 to the power of n. So how do I know from this question that I'm going to be using power series?
Because of the variable.
Yeah, that variable x, right? Now I'm thinking kind of ahead. I know after I find my center, I need to use one of the multiple tests that we know to determine my value of L. Which test are we thinking about here?
Root.
Ratio that.
Yeah, I would say actually not root. 100%
Ratio.
not root because of that n factorial. That's going to mean, hey, you should use the ratio test, okay? Because more things, they cancel out more things when you have the factorial and the ratio test, okay? So let's find our value for which x will converge, or for the value of x for which this series will converge. So we're going to set that 2x plus 1 equal to 0. And with a little bit of algebra, we've got x equals negative 1/2. Okay. So as long as we can find that this series converges with step 2, then we know that x equals negative 1/2 is a guaranteed value. Okay, but this is contingent upon the second one showing that it is convergent. So let's find our L. So I'm going to get n plus 1 factorial times 2x plus 1 to the n plus 1 over n factorial times 2x plus 1 to the n. All right, so based off of what we learned yesterday, we could break n plus 1 factorial into n plus 1 times n factorial. So this n factorial will cancel out with the remaining parts of that n plus 1 factorial, okay? And then this 2x plus 1 to the n will cancel with this one. And so what we have left is 2x plus 1. All right, we've got that part. We have our n plus 1, and that's all over 1. Okay. Now, the part with the variable we can bump out to the front, but we should keep it in absolute values. Unless it's a squared, then it didn't really matter as much. But in this case, it's just a linear function, so that 2x plus 1 should be in the absolute value bar, okay? And then we're taking the limit as n approaches infinity of n plus 1.
Diverges.
What happens to this part?
Diverges.
Yeah, this goes to infinity, okay? So here's what this means for us. The only way that we can get L to be less than 1, okay? Because remember, this whole thing is L.
When it's equal center.
Yeah, in order for L to be less than 1, if we know we have the absolute value bar, this thing has to equal 0. Does that make sense? Like conceptually here, that in order to get an overall value of less than 1, we take the infinite value we're going to get and we multiply it by 0. That'll get us under 1. Okay. And that is exactly right. This, if we solve this, well, that's exactly what we did up here. That the only value that makes this one true is x equals -1/2. Okay. So in this case, when we're trying to find our radius of convergence, since it's only the center value and nothing else, our radius of convergence is 0. And maybe next to that we can write because only one value of x makes this infinite series converge. Okay. So the one value we found in the beginning is the only value that makes it true. So if we were to write an interval of convergence, we wouldn't really have one. We would just say that the only value is just x equals -1/2, because the radius is 0, so there's no interval. It's just a single value, x equals -1/2. Okay. So hopefully we've seen a variety of questions here where some of them are definitely more work than others. But I think with these special cases, even though they look like less work on paper, there was a lot of conceptual understanding and implications that we had to make along the way so that we could get to these answers. Okay, so maybe like writing down work-wise, it wasn't as much work, but the kind of reasoning that we had to do, I think it does require a different kind of work. Okay. Are there any questions about example number 5? Or any of the examples that we've talked about today?
So for example number 5,
Yeah.
the reason why our radius is 0 and the interval of convergence is x equals -1/2 is because we set the absolute value of 2x plus 1 equal to 0, and that's the only value that makes it true in this sense.
Correct.
Okay. All right, cool.
Any other questions, folk?
Yeah, I have one question.
Sure, what's up?
Let's say that you were sitting there and you were trying to find out your value of L, and you bring out your x binomial, whatever it is, absolute value outside, and you take the limit of whatever you have on the inside, and that turns out to be 0. Will we run into a situation like that?
Yeah, so I think we saw one like that earlier. Was it example number 3? Yeah, this one, right? So this is sort of the other special case. So in this case, we did. we got that limit goes to 0. And so that means that your interval of converge, or your radius of convergence, is infinity, because any value you put in there could make it true.
Okay.
Okay.
Oh, yeah, because you need your you need the L's value to come out, or the absolute value to come out to be 0.
Mm-hmm.
Okay, that makes sense. And my last question is, if you are dealing with an alternating series,
Yeah.
and you have a term on the top that makes it alternating and a term on the bottom that makes it alternating, would both of those be pulled out, and whatever is left would be your B of M?
Usually there's only one term that creates the alternating. Have we seen one where maybe there's 2?
I was looking at the quiz.
Which quiz question?
I was on question number 9. It could have just been my algebra, but when I was plugging in my my x values, I was getting like a negative constant to the n power, and then you still had on the bottom your -3 to the 2 plus n.
I think maybe more things cancel. I would split, like, anytime you have the like a -3 to the n, I would split it to be like -1 to the n and 3 to the n.
Gotcha.
Does that make sense?
And then I could just take the negative out of the top.
Yeah.
Okay.
Yeah.
All right, thank you.
You're welcome. All right, folks. So if there are no other questions, I think that's it for today.